Swayam Prabha. Digital India. Educated India.
Hello everybody, welcome back. We're going to do something totally new today. We're going to do some synthesis. What does that mean? We're going to take stuff out there on a shelf that you can buy from someplace and make a new molecule. Why would you do this? Well, all of the pharmaceutical industry pretty much does this one thing, is synthesis, and you know how lucrative that is, right? So you take a readily available starting material and then do some synthesis on it. That means you change it step by step by step. And then you get to a product that's really valuable. It's got some monetary value, or medicinal value, or some kind of use. So that's what we're going to do. We're only going to do 2 steps, which is just like a baby synthesis, okay? But typically synthesis would be 4 or 5 steps in a lab. Some of the, getting Taxol from the yew tree extract was 40 steps. Each one would have different regiochemistry, stereochemistry, and it's an enormous procedure. But we're going to do some very small steps. Okay, let's look at some rules. I mean, these are not really rules. These are more like strategies, synthesis strategies. How do you approach it? Because if you stare at this long enough, this is not going to pop into your brain. It's not. You got to stare at this and try to, see how you can get there. That's more like it. So what's the first thing to do? The first thing to do is find the starting material in your product. So at least you know what changed and what didn't. So find the starting material in your product, and then you can see what are the changes. What are the functional group changes? What are the skeletal changes? Skeletal change meaning, for example, this is a cycle. This is an open chain. That's just a big skeletal change. Here, you're taking a molecule like this, you're still having the same skeletal structure. So there's no skeletal change. But there's been some functional group change. Obviously, the bromide went away and you're getting a hydroxyl in a different place. So how do you approach this? I mean, what do you do to do the functional group changes? What you can do is retrosynthesis, or work backwards. So you can have a molecule here that's formed, and you can see, well, what are the ways in which you can form that? For example, let's take this. The skeletal structure didn't change. And over here too, the skeletal structure is the same, but the functional group has changed, or the position has changed. So where do we even start? For retrosynthesis, try to make the target molecule from the precursor. That means if you go back 1 step, how would you make that from there? How would you typically make a tertiary bromide? We learned of having bromide additions to pi bonds. And if it's tertiary, it's Markovnikov. So that's pretty much the most obvious way to make it. So then we can do that and come up with an intermediate. And then we can see how you can get to the intermediate from the starting material. If there are multiple steps, then how do you form this from another starting material, and so on. Okay, so what you call a synthon for it. A synthon is where you have the functionality hidden and some action is going to bring it out. Okay, so we're going to make some synthons and go about doing synthesis on this in a reverse order. That's called retrosynthesis. So first find out what is it that changed, what is it that didn't change, and bring in the starting materials in the reverse order. Like start from the product and go 1 step at a time. Now, once you've done that, then you have to go in and fill in the reagents. When you do that, you have to be really mindful of the fact that there would be regioselectivity and stereoselectivity in these reactions. And whatever reagent that you put should give you the product as the major product. All right, we're not trying to make minor products here because we won't make any money making minor products. So we've got to make the major product. So it's got to be regioselective and stereoselective for the major product for the reagents that you're going to bring. Once you've done that, then you can draw in, fill it all in, and draw your intermediates. And if necessary, you can check the mechanism and see that it works properly, and as you have written. All right, let's go about it. Let's do the first thing here. So, well, here is your 5-membered ring with a methyl group here. And that's what we have here, a 5-membered ring with a methyl group. That didn't change. What changed? What changed is already written out in a different color, but I can mark it out for you. Your chlorine here became a bromine on the next carbon. All right, so we know what changed. And we know that we got a tertiary bromide. Let's explore how we can make a tertiary bromide. A tertiary bromide is when you have a alkene like this, and then you add HBr, you're going to get H here and Br here, Markovnikov addition. And that's exactly what we can do here, Markovnikov addition. We can add HBr to if you add HBr, H is going to go here and Br is going to go here. So it's a Markovnikov addition. If you had an anti-Markovnikov, let's say HBr peroxide, then bromide would have ended up in the same place as the chloride, but that's not what happened. So then we can say, all right, this is a Markovnikov addition and a tertiary, and that's going to be then your starting material. All right, so we know now that we need an alkene here. How do we make alkenes? Look at all the Rolodex of reactions in your head. Turn it around. What did you do? Alkenes are typically products of elimination. And what kind of elimination? E2, basically. E1 too, but E1 has a lot of SN1 and other side products, so that's not our first choice. Our first choice is E2. Just like in substitution, our first choice would be SN2 because we want to get clean, stereo-specific, regio-specific reactions. We want to get clean, regio-selective, stereo-specific reaction to enhance our yield. We don't want to have 25 side products and spend half our life in lab trying to put them through a column and separate them. And that takes, that can really drive you crazy. So you really want to make something that's going to go one shot as much as possible. And how did we do elimination? Just take an alkyl halide and use a base. Now we do have choices on base. Some bases only did E2 Zaitsev, and those were typically small bases. Some bases only did E2 Hoffman, which is anti-Zaitsev. So we have to figure out where would you want to have your alkyl halide if you want to do an E2 here. Well, you could put your halide here or here. Those are the only two choices. If you put your halide here, here, or here, you wouldn't get a double bond there, obviously, right? So of these, you already have a starting material with a chloride here. You want to do the most substituted alkene. Easy. So that's going to be just a Zaitsev. And for a Zaitsev, you can use a sodium methoxide. This is secondary. Secondaries give major E2, minor SN2. We don't want to put a bulky base like DBU or even COTBU because that's going to do an elimination here. We don't want that. We want the elimination here. So we want to put a small base. So let's say we have a small base, and you can have protic or aprotic as we talked about in E2, and we should do an E2. And so that is going to be, let's say, sodium methoxide, sodium methoxide. I'll just put sodium methoxide. That's kind of one of the most inexpensive bases out there. Heat. E2, you want to get more elimination than substitution. Heat it up. You're going to get more elimination. All right. So that kind of gives you a little flavor of how we kind of handle synthesis. synthesis. Let's look at the second one. Well, there's nothing. I mean, at first glance, it looks like they have nothing in common. But do they? Let's look at it. 1, 2, 3, 4, 5, 6, 7, 8 carbons. 1, 2, 3, 4, 5, 6, 7, 8 carbons. What's this CHO? Is that an alcohol? A lot of students look at that and think that's an alcohol. But really, when you write that out, CHO, so you have to put that pi bond in order to get a octet with, the rest of the chain. All right, so always remember CHO is aldehyde, always, especially, you see this in NMR and later on in a lot of things. CHO is not alcohol, it's aldehyde. Terminal carbonyl, which is an aldehyde. All right, let's look at how we can get to this. What did we talk about? What kind of reactions did we talk about to get ketones? Well, we got ketones from triple bonds when we hydrolyzed them, but it's impossible to make a triple bond here just because triple bonds would need a much larger ring. Even, you can have double bonds, but triple bonds would need larger rings. Just because it's sp and sp, you would need larger rings. So it's almost impossible there to get a triple bond over here. Well, what else gave us ketones? Well, we got ketones from ozonolysis. Is that a possibility? The easiest thing to see whether this is an ozonolysis is to take off these oxygens and make a double bond. So for that, we have to bring them close to each other. So bring the pi bonds or the carbonyls like this. You have hydrogen on one side, you have an ethyl on the other side, and you have, let's say, 2, 4, 6 carbons in between. 1, 2, 3, 4, 5, 6 carbons. Well, then let's say if you take this out and connect them like that, is that going to give you a pi bond? Yes, it is. So that's pretty much the answer there. So whenever you see 2 carbonyls on a line, or even 2 carboxylic acids, you could do that and say there was a triple bond. But if there was 2 carbonyls on the same chain, you should think ozonolysis as one of the first options to make them in one shot. Because it's impossible to put 2 hydroxyls and then oxidize them. So here's one way to do it. So we take these out, then we are going to have 2 carbons here and then 6 carbons. So this carbon and this carbon would be connected together with 1 pi bond. So if you connect those 2, that is going to give you a double bond like that. Now, what do we have here? Can we get that from here? Well, I'm going to draw it just a little bit rotated so you can see that. And, you can rotate this any way you like. This is the same thing as this. Well, what have you here? You have a alkene, cyclohexene, ethyl cyclohexene. How are you going to get that from here? The double bond is here, and you have an ethyl cyclohexene. So basically, you have to do an elimination just like we did before. Do we want to use DBU, DBN, third butoxide? No, because that would give you a Hoffman elimination. We don't want that. We want to get a Zaitsev elimination. So same as above. So we can put sodium methoxide, or some small base, and on secondary, that is going to give you major E2 small base. You may get some SN2, but if you heat it up, you're going to get more and more E2. So there you go. So that's pretty much how you do a open chain dicarbonyl from a halogen. Elimination and then ozonolysis. What do we need for ozonolysis? We are going to put in O3 DMF. This is going to be on an alkene. Let's look at this. Over here we have a bromine. Okay, we're starting with lots of halogens here. And we have an alcohol here, and it's not even on the same carbon, it's on the next door carbon, and it's a terminal alcohol. All right, so we know we can take this off and put an OH right here with SN1, just hydrolysis. That's not what we want. We want it on the next carbon. So putting it on the more substituted carbon is the one that we've done before more, a lot, because it's Markovnikov. But putting it on the furthest carbon here, or the less substituted carbon, that's going to be anti-Markovnikov, isn't it? So anti-Markovnikov addition. So the first thing is check the structure, skeletal structure is the same. So we didn't do any drastic ozonolysis, Kamenov for heat and so on. We just did a functional group change. So functional group change means you're taking one functional group, changing it to something else, and creating another one. And we're going to work backwards. If you want to put a hydroxyl here, well, what kind of functional group should you have here? If you had a halogen there, yeah, you could do an SN2. That's possible. What else can we do? Since it's on the less substituted carbon, we can think, anti-Markovnikov addition. And then the one that we learned about that did anti-Markovnikov involves boron. That's right. So we have borohydration. So that's one thing to notice here. Markovnikov, Zaitsev, these are all regioselective. Okay, this is also Zaitsev. Here you're doing anti-Markovnikov because you're functionalizing the less substituted carbon. And so then once you know the regiochemistry, then you bring in your reagents to get that specific result. We really haven't shown stereochemistry here. So at this point, just let's focus on regiochemistry. So if it's anti-Markovnikov, well, we did talk about anti-Markovnikov reagents. So the main anti-Markovnikov reagent that we talked about is boron. And we said we can enhance the selectivity by bringing that boron with even bigger groups. I mean, we did this a lot with the moose head with alkynes. You can also do that with alkenes. So BH3 THF, and then follow it up with a good, nice hydrolysis. Make sure you don't put the hydrolysis and the boron at the same time, because then it's going to attack the boron, not your reagent. H2O, and you're going to get anti-Markovnikov on a alkene. So for that to work backwards, we need the alkene right here and not inside. So we need a less substituted alkene. So that is going to be Hoffman or anti-Zaitsev. We cannot do Zaitsev here. If you did Zaitsev, you're going to get the more substituted alkene. How did we do anti-Zaitsev or Hoffman? We brought in huge bases that just couldn't get in here. So some of the bases only did E2, and those are DBU, DBN, even terbutoxide. So I'm going to put over here DBU, and you can put some, DMF or some solvent here and heat it up, and you are going to get anti-ZZF, it's called Hofmann elimination. Hofmann, which is anti-ZZF. So the opposite of what we did before. So we have to first be really mindful of the regiochemistry. Then you bring in the reagents in the appropriate way to do the reaction. So here we have anti-Markovnikov, anti-Zaitsev. For both of them, the reagents are different. All right. Now that we've done our regiochemistry, we can check to see if we have our intermediates right, and the whole thing's good. If you want, you can even do a little mechanism on the side to check sometimes if you have stereochemistry. That's a good idea to do. All right, let's look at the next one here. Did we do any skeletal changes? Let's see, isopropyl connected to an ethyl. Isopropyl, the ethyl is right here, but it's now a triple bond. It's not a CH2CH2, it's a alkyne. We have an iodine here, and that's gone. Well, how did we get to this point? Well, over here, what's the way to make an alkyne? Let's start from here. Let's start backwards. Okay. So let's do our retrosynthesis. So we have functional group change. Iodine became a triple bond. Retrosynthesis. Let's see how you can go back. How did we make an alkyne? What was the way to make an alkyne? There are two ways. We took either a vicinal bromo and did an elimination like this, or we took a gem dibromo and did an elimination with sodium amide in a NH2 excess. We could have used KOH and heat it up, or lots of strong base. All right, well, this doesn't really look like this. How did we get to a dibromo? Well, when we had a dibromo, we had an alkene and we did the anti-dibromo, remember? So to get to synthesis, you really need to know your reaction, otherwise you're going to be wasting your time. Or we could have done this too. How did we do this? Well, to do this, we could have taken a triple bond and added HBr excess to get the gem. To get the dibromo vicinal, we can take an alkene and do anti-addition. So then we got to find out, well, which one do you want to do? Well, we don't want to go to a triple bond, then make this and go to a triple bond. That won't make any sense. We want to go here because you just have to make an alkene and then take the alkene and dibromo that. All right, so at least we know what's before this. We don't want to go here. We want to go here. All right, so, well, how do you make an alkene? We've done this several times now. Just alkyl halide with a base. Now here, do we want to put a small base or a large base? What do you think? It's primary. If you put a small base on a primary, you get more SN2 than E2. So you don't want a small base. We want a large base. DBU is great. So let's put DBU or DBN, heat, DMF, DMSO, some solvent. Or you could also put potassium tert-butoxide and do a elimination right here. So you don't want to do sodium hydroxide, sodium methoxide to do this E2, mainly because that's going to give you more SN2 on a primary. So you need a large base. So both these need, when you have Hofmann, or in this case it's Hofmann elimination, here in this case it's a regular elimination, but still you want to get the terminal alkene, you want to use a large base, no SN2. That's why you want to do that. All right, so here we are getting along here. So you put this over here, now you want to do the dibromo, then you bring in your bromine, and you don't want any water, otherwise you're going to get addition with hydrohalogenation. We don't want that. We want to put aprotic CCl4, dichloromethane, either one of some aprotic solvent. I mean, we're trying to keep away from this because this goes in the chlorine radicals eat up the ozone in like a chain reaction. And so we have other alternatives, but this is probably what's in your textbook. So we're doing an aprotic solvent. That's what's important. It's aprotic and it's distilled to take off all the moisture. We don't want to do this. Great. So when you have multiple pathways, choose the one that will give you the correct regioselectivity and stereospecificity. Well, let's look at the next one. Here you have a sec butyl connected to an alkyne. And here you have the same sec butyl, but the alkyne's gone. And you got like a ketone and like stuff hanging off of here. First thing is, well, find the starting material. And you have 4 and 2 carbons. And here you have 4 and 2 carbons. Okay, starting material is there. It's not blown off. Good. But what happened to it? The triple bond became a ketone and it's got a tail. Well, how did you put a tail and how did you get a ketone? On triple bonds, we did both of them. We can put a tail, and we did put a tail by taking off that sp hydrogen because it's acidic and you know the whole story, and making an anion and doing an SN2. Great. And we did a ketone. How did we do the ketone here? Yes, we could do ketone on this carbon with mercury 2 plus and H2SO4 water. We could do a carbonyl on this aldehyde on this carbon with borohydration. Which one do you think you want to do? Well, it's on the carbon that's more substituted. So whenever you have more substituted carbon turning into a carbonyl, we said that use Markovnikov, which means you're going to do the sulfuric acid, water. Acid conditions are basically what triggers the Markovnikov reaction. So let's write that down. So we have 2 reactions going for us. So we're going to have this one reaction is taking this and doing an SN2. And so you have 1, 2, 3 carbons that are attached. So you have to bring the 3 carbons with like a leaving group, like say like a chloride, and doing an SN2. Great. And we are also going to do a hydrolysis to get a ketone. So if you take this and do H2SO4, HgSO4, sometime when you're doing this synthesis, you should have a scratch paper on the side so you can kind of write your thoughts down. You're going to get a ketone here. CH3, methyl ketone if it's a terminal alkyne. So, but the thing is, which one should you do first? So you have 2 processes that you're going to do. You're going to do an SN2 to append this. You're going to do a hydrolysis to get the ketone. Which one should you do first? Which one should we do first? Should we do the SN2 and then do the hydrolysis? Or should we do the hydrolysis and then do the SN2? If you did the hydrolysis, you'll get this methyl ketone. We haven't really learned how to do an R group attachment to this alpha carbon here. You will later on. So for right now, let's do this first, where you append this. Then you can, after you append it, you can hydrolyze it. But then you're going to say, oh, well, aren't you going to get a ketone here and here? What are we going to do with both ketones? In that case, you just say distill. That's it. Okay, because they're going to have different boiling points and you have to distill them. Okay, so let's write this down. We're going to first make the anion, and we did that with NaNH2. And you can put NaNH2 1 and then 2 alkyl halide, but since I have some space here, I'm going to write it all out. This is going to get your triple bond hydrogen removed, and you'll get an anion. And then your ammonia goes off with that hydrogen. Now you're going to take this and you're going to add to this your alkyl chloride, which is going to be 3 carbons. This is where it stops here. So here's going to be 1, 2, 3. So you don't want to bring more or less. Make sure you count your carbons before you bring that carbon, because it might look like it's a 4-carbon chain, but it's not. So here you can take this and do a backside attack, kick that guy off. This is perfect because it's primary. So that's the best choice for SN2. So you're going to get your propyl group now hanging on to that alkyne. Now you can do hydrolysis, and well, you do AgOAC, H2SO4 aqueous, and you probably heat that up. And then you could say, well, distill ketones. It's understood that you're going to get this, plus you're going to get the ketone where you have the hydrolysis on this carbon. And you won't really see much of a difference in the percentage distribution. All right, let's look at the last one. I changed it a bit just because we've already done the alkene migration. So let's do a different one. We have a bromine here, and then it became methoxide. Let's go through the rules. Hydrocarbon chain, pretty much here and here the same. The change is functional group. Your bromo became an ethyl ether. All right, so that's kind of nailed. Let's look at the next thing. How do we go about making this? What's the precursor to this? How can we make this? Well, we cannot do an SN2 on a tertiary. And if you bring an ethoxy base, for example, you might think, oh, why don't we do a nice SN2? It's not going to work, because if you take a tertiary center like this, we cannot do SN2, no SN2 here. Or you cannot bring OET as a base and do an SN2. This is not going to work. Okay, because this is tertiary, no SN2. So let's not cut it here. So we don't want this to be our synthons here, this and this. That's not a good place to cut. Let's try to cut it here. Let's try to cut it here. Can we bring synthons for that? This ethyl can come in as an ethyl chloride, yeah? Okay. If you have an ethyl chloride, that's primary, so you will do more SN2 than E2. Great. And so what's the synthon for this? We can have an alcohol, which we can then deprotonate and make it into an alkoxy group. For example, if you have an OH group, we can put sodium hydride, take off that hydrogen, make it into an anion. So this could be, the OH can be your synthon. Then you can deprotonate and do an SN2. This will work. Why? Because this is primary. This ain't going to work because it's tertiary. Okay, so you have to make sure you're paying attention to stereospecificity, regiospecificity, and so on. You can't just dissect anywhere. There's a certain place that you have to take apart and bring together because of the regioselectivity, the sterics, the electronics, and the strains, and so on. Okay, so you got to pay attention to that. So our next goal would be to go from here to here. How do you take off a bromine and make a hydroxyl here? Well, we could take off a bromine and, well, if you can't really do an SN2 here because that's going to put the hydroxyl here. In order to put the hydroxyl here, look at this. This is the most substituted carbon. If you want to put an oxygen on there, that's Markovnikov. And we did Markovnikov hydration on alkenes to give you tertiary or more substituted alcohols. So that would be the way to go. So you would want to have an alcohol right here. And to do that, you want to do Markovnikov. In order to do Markovnikov addition, you need a pi bond. You can have a pi bond here or here or here. All of those would only give you a hydroxyl there. So here we want to have H2SO4, H2O, Markovnikov. You don't want borohydration or anti-Markovnikov. So this is what we're going to do. In order to do that, we need to have an alkene. And as I said, your alkene can be internal or external. Looking at this, which one do you think is more likely? Of course, if you're going to do an elimination, you're going to get your double bond right there. So the precursor to that, or the synthon, would be a pi bond right here. Well, how do you do a pi bond right here? We got to do an elimination on that, HBr elimination. Now you're going to do an HBr elimination on a very crowded spot there. So what do you want to do here? Do you want to put a large base or a small base? Remember, this is primary. If you have a primary and you put in a small base, you're going to get SN2. So we ain't going to do that. So small base with primary is going to give you SN2. And that's not what we want. Therefore, we're going to put a large base. And let's say we put in T-butoxide, COT-BU, and COT-BU alcohol, so T-butanol, and then you heat that up. That's going to give you an E2 right here. Then you do a Markovnikov hydration to put your alcohol right here. Then you're going to do a sodium hydride to get rid of that proton. So you can put some base. Sodium hydride would be a good one. Sodium hydride, H minus is going to pull off this hydrogen and give you this plus H2. So you'll have a sodium here. That's going to do a backside attack, SN2, on a beautiful primary to give you that. Okay. All right, so that's a very nice way. So the alternate method to this would be to take this and treat this with MCPBA, and that's metachloropurbenzoic acid, which is just a peroxide. That's going to make it into an epoxide. And let's say you take that and then you make the epoxide. Now you can open this up with a hydride. Let's say lithium aluminum hydride, and that is going to then give you the hydrides. It's going to go for the less substituted carbon. So that's another way to do it. So let's say you have two possibilities like this. Which one should you choose? You're going from A to B, and there are two pathways. Choose the one that has fewer steps, because fewer steps would mean typically a higher yield, because every time you do a step, you're losing some of your product, right? So you're going to lose some. So the fewer steps would be better. Also, it's less time consuming. Two, if you have two of them having the same number of steps, so this has got 2 steps and this has got 2 steps, they're just going through 2 different intermediates. Which one should you choose? Choose the one that's cleaner. I mean, when you put H2SO4 and heat it up, you might get elimination inside the ring. You might get side products. So we try to keep away from these acid refluxes as much as possible. MCPBA is pretty clean. You can only get epoxide here. There's no real rearrangements here, and that's pretty good. So I would, going between these two, you would choose MCPBA. Whenever you have side products, try to avoid them. This is clean. Over here, sodium hydride, and this is a lithium aluminum hydride. They're kind of similar. This is a ring opening, which happens really nicely. So I would pretty much go this pathway over this. Okay, not that this is wrong, but you might get a higher yield here. And in industry, that's pretty much what you're looking for, right? Product is profit. So that's something to bear in mind when you do synthesis. You may have lots of alternate pathways. Choose the one with the fewer steps. Choose the one with a higher yield. Choose the one that's cleaner with less side products. All of this is going to give you a really nice, expedient way of transforming a certain molecule into a totally different molecule. All right, we'll come back with more synthesis to give you some more practice. Talk to you soon. Bye.